Hello and welcome to this latest online resource to support GCSE physics. So today we're going to do our third lesson and we're going to look at how lenses work and also follow that up with how they're used. Our expected outcome today range from grades 5 to 7. For a grade 5 you'll need to identify real and virtual images by using ray diagrams. For a grade 6 calculate the magnification of a lens, use it based on the object and image size. And for a grade 7, you need to explain ray paths through a lens in terms of reflection and the focal point, and you also need to perform calculations involving the rearrangement and change of the subject of the magnification equation. Okay, let's begin by asking ourselves the question, what is a lens? Well, lenses are made of transparent material and they work by refracting light. So this happens both when the light enters the lens and when it leaves. So we've got two types of lenses that we're going to look at today. First of all, we've got the convex lens or a converging lens. What this does is make light rays converge behind the lens. So here we see the light rays coming in, and when they hit the lens, they're going to refract and they converge on a central point that is behind the lens. Now that central point is called a focal point or principal focus. That's an important key term that you must know, and you need to identify it on a diagram such as this one here. Convex lenses are what we use to magnify things, so they'd be used in magnifying glasses or in glasses that we would use to aid eyesight. Secondly, we've got a slightly different shape of lens. This is the concave lens. Now, the way I always used to remember this is that this lens bends inwards like a cave as opposed to the convex. So a convex lens works in the opposite way to the concave lens. The concave lens diverges or spreads out light rays. So here we can see the light rays travelling and hitting the lens, and this time they spread outwards. Now what this does is change where the principal focus or focal point is. Instead of with the converging lens, we actually trace out from where the lens rays diverge, so the principal focus or focus point is in fact in front of this lens. Now concave lenses are also used for glasses and they would be used to correct for short sight. Here we're going to look at how you can investigate a converging lens to find the focal length of that lens. You need to use a ray box, you need to use a convex lens which has got a holder which will allow you to shine light through it, and you need a screen upon which you can form an image. Now you quite simply shine a single beam of light through that lens and move the lens backwards and forwards in relation to the ray box until we see a sharp image formed on the screen. Once you've done that, that will allow you to measure the distance between the lens and the screen here, and that will give you your focal point or your focal distance. You can also consolidate that by looking at the YouTube link that I've put at the end of this slide. Now this image is real because it can be formed on a screen. Remember when we looked at last lesson and mirrors, we discussed the fact that a real image forms on a screen. A virtual image is one that isn't forming on the screen, it just appears to be there. Now the other thing you can do is look at magnification with lenses, and that's what this diagram down here, figure 5, is illustrating. Now basically, if you put an object in front of the lens, so in this case we've got a giraffe, and we allow that image to be refracted, we'll get an image formed on a screen, or we can see that image inside the lens. Now if you move the lens so it's closer to that object than its focal point, so instead of it being the lens being here, we've moved it to here, we can see that the light rays cross over. When those light rays cross over, that means that our image is larger, so we've magnified it. It will also appear upside down because of this crossover of the light rays. You may be required to calculate the magnification of an object by the lens, and you do this by dividing the image height here by the height of the actual object itself. That will give you the magnification. Now, what is important is that you make sure that the units you use for both these things are the same. So for example, they may both need to be in meters, centimeters, or millimeters, which means you need to be able to interchange between centimeters and millimeters, meters and centimeters as well, to be able to do this correctly. At higher tier, you may also be asked to change the subject of the equation. So for instance, if you want to calculate the image size, you would use this triangle, cover up the eye for image size, and that tells you that you need to do the actual size of the object times the magnification. Similarly, if you want to calculate the actual size of an object, you may need to divide the image size by the magnification. Next, we're going to look at using lenses and how to draw a ray diagram correctly for the two different types of lens. So we're going to start off with a convex lens, the one that curves outwards, and remember that will converge light rays to form a real image. So there's a key term that we need to know, and that is this idea of the principal axis. Now this here is the principal axis of this lens. It's basically a lens that runs at 90 degrees to the lens and right through the center. So we say the lens is upright here, this line is at 90 degrees and moving right through the center. So this is the principal axis. Now normally if you were drawing this lens, you would just draw it as a straight vertical line. There is no need to draw it as this convex lens shape. So if we know the position of the object and we know the focal length of this lens, we are then able to draw a ray diagram which would show the nature of the image that gets formed. So here we can see, first of all, we draw ray 1, which is parallel to the principal axis from the top of the object. That is refracted and it will refract through the principal focus. Ray 2 will pass through the center of the lens through the principal focus, and finally our ray 3 will pass through the principal focus before it reaches the lens. So here we see it passing through the principal focus, hits the lens here, and that will refract, so it is parallel with the principal axis. Then we see the points are converged here, so that's the top of the object. This is the bottom of the object, which has gone right through the center. So we therefore see that our image is this distance away and it is smaller than the original object. So this image has been reduced. Next, we'll take a look at how lenses can be used practically. So we'll start with a convex lens. If you place an object in between the lens and the principal focus, so that's here, and we imagine we've refracting the light rays that come from that object, like so. Those light rays enter the eye. The eye makes the assumption that they travel in a straight line, so to here. So this is where we see the virtual image of that object formed. And we can see that that virtual image is upright and it is also much bigger than the original image here. So what we're seeing here is this lens acting like a magnifying glass. So for instance, this would be how reading glasses work. If we look at a concave lens, we have the same principle, but this time the object must be further away than the primary focus not closer to the lens. And in this case, we have an object with light rays entering the lens and diverging, because we're talking about a concave lens. And if we remember, the virtual image is formed in front of the lens, and we can see in this case that the object is this tall, the image is this tall, so this lens has actually produced a smaller virtual image than the original object. So for the case of a concave lens, the image is virtual, it's upright, but it is smaller. So that concludes our work looking at lenses today. I hope it's been very useful for you, and I'll see you again soon with another presentation.